Welcome to another video on mathematical logic, still studying propositional logic, and in this video I'll do a couple of exercises at the end of the section, in particular exercises 1.1.11 and 1.1.13. So the first exercise that we're going to do is this exercise to show that no proper initial segment of a sentence is a sentence. So to explain what this is even saying, let's talk about what an initial segment is, and then we'll talk about what a proper initial segment is. It's somewhat intuitive from the name. So if we take, for instance, this sentence, negation arrow P1, negation P2, then if I were to take just the first several characters from the expression, that would be an initial segment. So an initial segment is just some expression which is shorter, perhaps, than the expression and has all the same, first several characters. But the thing is, what if I were to take all of the characters? Then that still technically is an initial segment. But, so let's copy these initial segments over, right? So this is one initial segment of the given expression. This is another one. There are many others. But this is the one that we're ruling out when we specify that we're talking about a proper initial segment. So a proper initial segment is an initial segment that is not just the whole expression. So that's what a proper initial segment is. The exercise, or the claim that we're going to be proving, is that if you take a proper initial segment of a sentence, you do not have a sentence. So if I were to take this proper initial segment of the sentence, that is not a sentence, and no other proper initial segment of this sentence is a sentence. So we'll be proving that for all possible sentences. So the proof that we give is going to be by regular induction on the length of the sentences. So not induction on complexity, but induction on a natural number n. We'll start with n equal to 1. But in any case, as a note about notation, when I do this proof, I'll use that script L symbol to be the length of a given string. So in the proof, by induction on the length of a sentence, we'll take n equal to 1. So we want to show that if any sentence has length 1, then no proper initial segment of that sentence is a sentence. Well, when the length is 1, you're dealing with just an atomic sentence. It's just a single sentence letter. Any proper initial segment of that is going to be the empty expression, and that is not a sentence. If you need to prove that that's not a sentence, that's an easy exercise, but we could just, for the purpose of this exercise, take it for granted that no, or the empty expression is not a sentence. So there's the base case. So for the inductive case, we'll start with the inductive hypothesis. And for us, that's going to be that if you take any string of length n, or even less than or equal to n, but in particular n, take any sentence of that length, then it has no proper initial segment, which is a sentence. So that's the inductive hypothesis. We want to use that to prove a corresponding fact for n plus 1. That if you take a sentence of length n plus 1, that no proper initial segment of it will be a sentence. So that's the goal. That's the setup. We want to consider any sentence of length n plus 1. We're going to call it psi. And let's break this into several different cases, right? If its length is n plus 1, then it has length at least 2, so it's got to have a connective symbol at the start followed by something else. So let's start with the case where that connective is a negation. So by the unique readability theorem, we know that we must be dealing with psi equal to negation theta. Theta is a sentence. We want to take a proper initial segment of that, call it x, and we want to prove that x cannot be a sentence. Well, if x is the empty expression, there's nothing to prove because, as we've already said, that's not a sentence. So if it is non-empty, it must lead with a negation and followed by some other expression, call it y. Note that that y could be the empty expression, so there is no worry about am I necessarily missing a possibility or something like that. If we allow y to be the empty expression, then we're not missing any possibilities. Now, because x is an initial segment of psi, then we can sort of cancel the negations on each of these and say that y, and I mean a proper initial segment, y is a proper initial segment of theta. Therefore, y is not a sentence by the inductive hypothesis. Therefore, x is negation y, where y is not a sentence, and therefore x is not a sentence by the unique readability theorem. If it were a negation of a sentence, right, like if x were a sentence and it leads with a negation, then what's under the negation must be a sentence. But here we know that's not true. Okay, so there's the negation case. So we move on to the binary connective case. In this one, we'll assume that psi is bullet theta eta. Bullet is some symbol for any binary connective and or arrow, so on. Theta and eta are each sentences. We'll again assume that x is some initial segment of psi. If x is the empty expression, there's nothing to prove because that's not a sentence. And otherwise, x leads with a bullet, so we can write x as bullet y for some expression y. And our goal now, which is slightly more complicated, is to prove that y is not the concatenation of some two sentences. We will try to prove this by contradiction. So for contradiction, and here's a little contradiction symbol, two arrows colliding. We will assume that y equals alpha beta, where alpha and beta are some two sentences. And to arrive at a contradiction, we're going to consider three cases, all of them having to do with the length of alpha and phi. I see that I have a typo here in the slide in the last one where it says L of alpha greater than phi. That should be length of phi, but anyway. So we're going to look at these three cases, and in each one show that they lead to a contradiction, so that proves a contradiction overall. In preparation for that, let's note that the length of alpha, the length of phi are both less than or equal to n, right? After all, in each case, it's coming from a string of length at most n plus 1, and we are dropping at least one symbol. So they must have length no greater than n. And therefore, the inductive hypothesis applies to both of them. In fact, it also applies to beta and to psi. So it's really, it applies to every one of the sentences that are in play at this moment. Okay. Let's now look at the three cases. In the first case, we assume that the length of alpha is less than, strictly less than, the length of phi. This makes alpha a proper initial segment of phi, and that means since phi satisfies the inductive hypothesis condition, no proper initial segment of phi is a sentence. So alpha is not a sentence. But we had assumed earlier that alpha was a sentence, and that's our contradiction. Moving on to the next possibility, if I swap them around, then really I can say exactly the same thing with everything sort of swapped around. If the length of alpha is greater than the length of phi, now phi is a proper initial segment of alpha. Alpha satisfies the conditions for the inductive hypothesis. Therefore, no proper initial segment of alpha is a sentence. So phi is not a sentence, but from our earlier assumption, phi is a sentence. Finally, if the lengths of alpha and phi are equal, then you can imagine, right, we know that essentially alpha beta is a proper initial segment of phi psi, right? And so if alpha and phi have the same length, and alpha is, and this is a proper initial segment, then alpha just is phi. And therefore we can cancel these characters and infer that beta is an initial segment of psi. So now that we have that beta is an initial segment of psi, well, we can again apply the inductive hypothesis to psi, seeing that no proper initial segment of psi is a sentence. Therefore, beta, being a proper initial segment of psi, is not a sentence, but we assumed earlier that it was a sentence. There's a contradiction. And so now this proof is complete, right? The whole induction is complete and so on, so we're all done. Okay, for the next exercise, we're going to look at a few example sentences and decide whether or not they are sentences. So, I might as well just present this kinda in a systematic way, even when we don't really need it, just to see that there is a system that we can use here. So let's take this first expression. We don't yet know that it's a sentence. And here's what you can do. If this is to be a sentence, then we must be able to identify this, right? If the first symbol is a negation, then everything after it must be some sentence. So now we need to show that this is a sentence. Now, in order for this to be a sentence, we see that it leads with a disjunction, and so there must be some sentence written immediately after it. And we could not stop at the negation. That would not be a sentence, obviously. We could extend to negation P1. That is a sentence, somewhat obviously. So there is our first sentence. From there, we need to show that everything after that is a sentence. And there we have it, right? P2 is an atomic sentence, so it's immediately a sentence. We've shown that the disjunction is a sentence, and then the negation of that is a sentence. So we're done. The first one is a sentence. Let's look at the next one. Let's do this all over again. So we take P1, P2, negation P3 like that. Okay. Again, we read left to right. We scan a conjunction symbol first. And we say, okay, whatever comes after the conjunction symbol, I must grab a sentence. And I'm done immediately, right? P1 must be the sentence right after that. And then I must have that whatever follows it is a sentence. But we can see that this is not a sentence. And one nice way of seeing that this is not a sentence is to see that an initial segment, a proper initial segment of it, is a sentence. Namely, this part right here, that's a proper initial segment, which is a sentence. So I can actually refer to the theorem that we just proved a moment ago. You know, if the large box here were a sentence, then you could not have a proper initial segment, which is a sentence, but it does have such a thing, so the entire thing must not be a sentence. So there we have it, right? So this is not a sentence. Okay, moving on to the next one. Let's do it all over again. Arrow, conjunction, P1, P2, disjunction, negation P3, biconditional P8. The arrow that leads the entire thing must be followed by a sentence and then another sentence. So we need to start here and close this paren at the end of some sentence. Can we stop at the conjunction? No. Can we stop at P1? No. Can we stop at P2 or just after P2? Yes. That's a sentence, somewhat obviously. So we have the first sentence in the conditional. Now let's find the second sentence. We need to argue that this is a sentence. Now, to do that, let's notice that the first symbol is a disjunction. So right after the disjunction, I must read a sentence. So can I read just the negation as a sentence? No. Can I read the negation P3 as a sentence? Yes. So that is the first sentence in the disjunction. Everything that follows must also be a sentence. So the first symbol is a biconditional followed, somewhat obviously this is a sentence. And so we're done, right? Everything checked out, sentence, sentence, therefore this is a sentence. Sentence, sentence, therefore this is a sentence. And then since this is a sentence and this is, therefore the whole thing is a sentence. And we're done. So yes, the third one is a sentence.